So we move on to Gerry's talk. So Gerry, if you're happy to share your screen.
Okay, just a second.
So while Gerry is switching on, so he'll be talking about simultaneous observations of a stellar flare or stellar flares in radio and white light bands with TESS and Australian Square Kilometre Array Station, I guess. So Gerry, you'll have 15 minutes, and please bear in mind that there will be a few questions in the end. Thank you very much.
Right. Okay, I'll be brief, maybe 10 minutes. Okay, this is basically a follow-on talk from what Gavin was presented. I'll mention some tests with some radio data. This work is being led by a PhD student, what Gavin and I are joint supervisors with our colleagues in Dublin. The movie you see playing right hand side is a movie taken from one of the instruments on SOHO. SOHO was launched in 1985. Some of the instruments are not working any longer. The chronograph is working. Since the mission was launched, it has detected in excess of 13,000 CMEs. That solar maximum is basically 2 or 3 per day, while solar minimum is typically 1 or 2. What we were interested in looking at is basically CMEs. Do CMEs occur on other stars, particularly M dwarfs? Okay, you've already seen some of these curves. Look at the top right-hand figure. That's Gavin showed you something very similar. You see the spot modulation with the flares superimposed. The middle panel, there's a blow up of quite a large flare with a 2-minute cadence. The one on the bottom right is a high cadence observations of another very active flare star called YZCMI, obtained with sub-second cadence. This object showed very short-term oscillations to the order of maybe 20, 30 seconds. Now, as Gavin already mentioned, 80% of the objects in our universe are basically M dwarfs. For many years, when I first came to Armagh way back in the early 1980s, when you wanted to observe M dwarfs, you had to apply for telescope time. You spent 1 or 2 weeks stuck on top of a mountain. If the weather was good, you may be able to observe 1 or 2 flares. I've been at different observing trips when I've been away for 4 nights and never even opened the dome. Kepler and TESS have really entirely changed that. The objective of Kepler and TESS was not to observe flares on M dwarfs, but basically to look for exoplanets. But as Gavin has already shown, Kepler observed M dwarfs for a period of several years. TESS now basically observes single objects for maybe 27 days. Some of the flares you get there tend to be of the order maybe 1,000 plus times more energetic than that of the sun. Now that's basically the radiation. But what about coronal mass ejections? What about particles? If on the sun, basically on the sun, most large flares have a coronal mass ejections. It's not entirely 1-to-1, but mostly. So what happens with these extremely large, 1,000 times more energetic flares on all the stars? Do we or can we see coronal mass ejections? The image here in the top right-hand corner is an image taken over about 60 seconds. It shows a type 2 solar burst. If you look at very closely up at the very top, I know the image is a little bit fuzzy, from 1,000 to 1,200 megahertz. You can see these oscillations. You probably see them better down at the bottom of the curve. What we are interested in doing is basically looking at M dwarf to see, can we observe something like this on an M dwarf? We're basically looking for type 2 radio burst or even type 4 radio burst. Now, as I said, normally you would apply for telescope time at a radio facility and a ground-based optical facility. However, TESS basically, since it observes a very large field of view, it allows you to observe not only a single target, but maybe several targets. So we applied for time on the Australian Square Kilometre Array Pathfinder mission. It's got 36 antennas. It has a very large field of view. It operates from 700 to 1800 megahertz. So we were given time on that instrument. TESS had already observed the southern hemisphere the previous 2 years prior to that. So we were able to select a region which had many M dwarfs. The region that we selected had a order of 40 plus active M dwarfs. So whenever we get 2 times 13 hours from the radio facility with a 10-second time resolution, the images, if you look at the image on the left-hand side, that's image taken in I. On the right-hand side is image in V. The first two, the first and second, you don't see anything in V. There's no right-hand circular polarization, while the other two have weak emission. We believe that most of the radio emission is basically gyrosynchrotron. We did detect, I'll show you very shortly, we did detect a short radio burst, which we thought was probably electron cyclone measure emission. We haven't already showed you some of the light curves. If you look at the top series of images, the first two is the spot of evolution. The third object has very little spot of evolution. The second row shows the radio emission. Now, in the radio emission, we do see small bursts. However, we do not see anything or very little in the optical. The first object on the left-hand side, we may see at R6 a very small increase in the optical. The question is why? I mean, do these stars have very strong magnetic fields which basically stop or inhibit coronal mass ejections? Or maybe TESS is basically too red. Perhaps some of these events are just more in the ultraviolet or blue region. I mentioned that and for one of the objects, we did see a very short right-hand circular, 100% circular polarization event. There's a quite short duration, quite faint. The signal noise wasn't great. This may be a CME. I don't know. It's probably electrocyclotron measure emission. Again, the observations are not conclusive. We have a second run. The run was a shorter run, this time using LOFAR for over 8 hours with TESS. We know there are several objects within that field of view. We also have a very, very long run on an extremely active M dwarf, 48 hours. We have ground-based U-band data. The U-band data shows several small flares. However, we don't see anything in the radio at all. So again, the question is, does the plasma really escape from the star? The images on the right-hand side, if you take a look at the middle image, this was taken with the Irish LOFAR station. It shows a really excellent example of a type 2 radio burst in the sun in May 22. I show on the right-hand side a small 3-minute section which shows a series of oscillations, quasi-period oscillations. This data is only just been analyzed, so check things out in a few months' time. We have some very interesting results. The future, I'm not sure if using these nursery wideband arrays is the best way. We may have to, if there anybody out there who has access to a radio telescope, we would be very interested in working with you, perhaps at a more targeted, so that we could pick an extremely active M dwarf with a very high probability of flaring activity. The example on the right-hand side is observations taken with a radio telescope, basically similar to the Australian. It's based in South Africa. This was taken for the active flare star called UV Ceti. It does show basically similar to the type 2 radio burst. You can see in blue, the blue emission basically is right-hand circular polarization, while that in red is left-hand circular polarization. It does change with frequency. So perhaps perhaps we need to have another look at this, but looking at from basically targeted observations as opposed to multiple objects. That's me finished, Brooks.
Yes, wonderful. Thank you, Gerry. And we have good 5 minutes for questions. Please, who wants to go ahead? Either raise your hand or just unmute yourself and speak up. So while I see your hand is up, please.
Can you hear me?
Yeah, I can. Yeah.
Okay, Gerry, thank you a lot. No, maybe from a theorist's point of view, I would comment the conclusions, so which is on the left top part of your slide now. Well, I think in any case, so the magnetic field in any corona should be, say, partly closed, partly open. So because it should be drugged with the stellar wind. So hence, possibly we can't imagine a situation when the magnetic field stops the ejection. On the other hand, if the magnetic field is high, I mean, so the absolute value is high, it means that so we should expect a lot of magnetic energy which could be released in the form of reconnection or whatever. So hence, I would rather say expect that you were not lucky. So and that actually more magnetic field in the corona, so more potential for eruptions and flares, I would expect.
Yeah, but the field strengths for these M dwarfs are several kilogauss, 2, 3, 4, 5 kilogauss.
No, yes, so a bigger body falls down louder.
Sorry?
A bigger body falls down louder. I mean, so we have more energy, so we have more energy for release, to be released, I would expect. Because I can't imagine that, so the corona remains fully closed. And so there are no events of openings which are accompanied by eruptions.
Yeah, the only thing I say about other groups have used blowfire, they've used different radio facilities for an extended period of time. And the number of possible CMEs is more or less zero at the minute. So the question is why? I mean, why? What is? I fully understand. I'm only suggesting it's because of the extremely high field strength. We don't see these things. No, maybe there are other reasons.
No, by the way, so maybe just a kind of naive question. Are you aware of any attempts in the radio band to distinguish between so the emission from open and closed, say, magnetic field regions? So because, all kinds of radio types should look differently in, say, open structures and in loops like or diffuse corona closed. Okay, maybe just thinking aloud, so possibly we can discuss it later.
Yeah. Okay.
Okay, thank you, guys. So I see one more question from Abhishek Srivastava in the chat. So Abhi, do you want to ask it yourself, please?
Hi, Gerry. So do these CMEs fail somehow there in the corona of the stars? That means because people observe CME signatures by dimming, so I think there is no dimming kind of things in some observations.
Yeah, they have. Okay, people have looked at things like H alpha, for example. I'm not convinced that the problem is we've only used radio plus optical, or very small, a red band in the optical. I think we probably need a more integrated campaign in which we have H alpha, and with if H alpha, then you can measure the active flow, how if there is a mass ejection, is it going at 200, 300, 400, 500 kilometers a second? So I think the observations that we've done yet will probably not give us the actual answers to these things. But the thing that's to go back to the previous question was why do our observations and others not show any evidence or little or no evidence of coronal mass ejections? Because these stars produce these flares that could be 1,000 times more energetic than the largest flare from the sun. Now, as regards how it was a question earlier on to Gavin, the accuracy, I think the accuracy of these is probably only a factor of 2 to 4, because we have to assume a black body temperature, and of course during a flare the black body will change but we're not out by an order of magnitude. So even if it's 10 to 35 as opposed to 10 to 36 ergs, it is an extremely large event. So, I mean, naively, I would expect some disruption or some sort of a plasma ejected from the object.
Okay, Gerry. Thank you.
Thanks, Abe. Thanks, Gerry. So, and like a quick comment from myself. So, I think it would be extremely interesting to put this apparent lack of CME signatures in radio observations in the context of prominence observations in stellar corona, because there are indirect observations of prominences and their dynamics in the solar, in not solar but stellar corona. That's exactly the point. Would be interesting just to compare so the statistics between these two.
Yeah.
So Ivan, I see Ivan also has a question. So Ivan, please be very quick.
Okay, just maybe a stupid question. What is the expected plasma frequencies in that M star? And is it possible that you don't see radio emission because of some like suppression mechanism of radio just cannot go out from the corona? Just if you
I don't know, but we have observations. We have observations from the VLA taken at several gigahertz. We have observations taken in with present observations at about 800 megahertz. We have low-power observations taken at 150 megahertz. Yet we see nothing. So I'm not sure if it's the frequency of the observations.
Okay, so